if I try to orient the net in this direction, in the horizontal direction. Hello viewers, welcome to Triveni Teachers Vidyapeth YouTube channel, and today I am up here to discuss about the topic of the chapter Gauss's theorem, and the name of the topic is electric flux. So basically this is the second chapter of the chapter electrostatics, and in this video we are actually focusing on electric flux. So let us start. So before we start, I want to ask you a simple question, that can you find out the area of this ABCD parallelogram? Yes, you can find out the area by multiplying this AB, the base, and the perpendicular distance between AB and CD. So let this perpendicular distance be DE. So we can write AB into DE. Okay. Now what is this DE? If this angle is theta, this angle is also theta. So what I can write? I can write DE equal to BD sin theta. So area of this parallelogram equal to AB into BD sin theta. So what does it mean? That it means AB into AC. Now if I write this in vector form, we'll write sin theta over here. So that is equal to AB cross AC. Now let us just quickly give a name. AB equal to our vector A and AC equal to vector B. So what does the area means? Area equal to A cross B. Now in order to calculate the magnitude, we have to calculate the mode of this vector. But here we are getting a point that area is actually not a scalar quantity, it is actually a vector quantity, because after cross multiplication of two vectors, that is A and B, we are getting this area. So area is actually a vector quantity. So this is clear from this discussion. So if a student of class 9, class 10 come and ask me, sir, is area a scalar quantity or vector quantity? What will be my answer? My answer will be obviously area is a scalar quantity. But a student from class 12 come and ask me, sir, area is a scalar quantity or vector quantity? My answer will be, it's a obviously vector quantity. So definitely area have a direction. So what is the direction? Now in order to understand the direction of vector, I have to draw few diagrams. Now let us consider few area. This is area A, this is area B, and this is a sphere. Now here we can see the upper surface, the area is actually horizontal and this is the upper surface. So this is the direction of the vector. We represent this by n cap, unit vector along upper direction. So in the lower direction also area must have another vector. So this is minus n, opposite vector. So both the cases the area have two direction. Now here also n cap, in the left and right also minus n cap. So in both the cases this area have two vector. So it doesn't matter in which direction you want to take the vector, either left or right, because area have two surface. So upper or lower, here left or right, you have every right to take any direction, there is no problem. But there is a problem in this third case where we are considering a sphere. Here we are considering a sphere, and in that case whenever you want to take the area vector, it must be always in the outward direction. You cannot take the area vector in the inward direction. So this is the problem. Why? Because these two are the case of open surface, and this is the case of closed surface. So in case of open surface, you can take the vector component, the direction of the area vector at any direction, either upper or lower, either left or right. But in closed surface, here you can see it's a closed surface. So in closed surface, you have to take the area vector always in the outward direction, not in the inward direction. So this is the center O. So this is the radius. So the area vector, if you take an area vector, it will be always in the outward direction. Is that clear? Now these are the things you need to know about this area vector. Now how to represent area vector? If A is area vector, this area vector have magnitude A and the direction that is represented by n cap, that is already we have represented. So direction of the area vector is always represented by this n cap. N represents the normal. Normal to which? Normal to this plane surface. N for normal, here the normal is with respect to the plane. Okay. So if we consider this whiteboard, what will be the area vector of this whiteboard? So area vector of this whiteboard, so this is the portion of a whiteboard, this whiteboard only where I am writing. So area vector will be in this direction. So this is the n cap. So amount of area, if we measure this length and that length, if this is A, this is B, the amount of area A can be calculated by A into B, and what will be this n cap? N cap will be this vector which is represented by this pen. Is that clear? Now let us move on to next point, that is solid angle. So we are going to learn about solid angle. Okay. So solid angle. Now what is solid angle? Sir, we already know what is angle, but what is solid angle? See, the concept of angle is two-dimensional, but in case of solid angle, it is the concept of three-dimensional. We'll quickly understand this by the example of watermelon. Okay, so let us consider there is a watermelon. Okay, so it's summer time, so I really like to eat watermelon. So this is a watermelon. Now if the radius of this watermelon is r, what is the surface area of this watermelon? This is 4 pi r square. Isn't it true? Obviously. Now if we take half of it, half part of the watermelon, so here also we are just cutting it by a knife and we are taking half part. So this is radius r. So here, so this is a half. Okay, so this is 2 pi r square. Isn't it true? Now if we just take quarter part of it, 1/4 of the watermelon, so here also this is r, so this is a 1/4, that is pi r square. Okay, so as you can see, all the cases or any other cases, if you just try to calculate the area, it is always proportional to r square. So area is proportional to r square in every cases, whatever be the area we try to calculate. So greater the radius, greater amount of area will be there. We'll just try to understand by comparing a cone. Okay, cone means where you try to eat your ice cream. Okay, now this is a cone. Now it generally like to put ice cream over here, isn't it? Now here two radius I am taking. This is r1 and this is r2. Now this area is a1, this area is A2. Now, if I tell you, so find out the ratio of A1 is to A2, what will be your answer? As I said, the area proportional to R square, so your answer will be it is R1 square is to R2 square. Is that clear? So from this concept we get the concept of solid angle. Because why you are getting this ratio? Because this is a part of cone and here the solid angle is constant for them. So as the solid angle is constant, we are getting this ratio. Solid angle generally represented by omega. Okay, we generally try to represent solid angle by omega. Now, how we represent a solid angle? Omega equal to ratio of the area with respect to the radius square. So area is dA and radius square, so r square. So this is how we generally try to represent the solid angle in differential form. Later I will discuss about why we try to always represent the solid angle in differential form. This is another point, but for this timing please remember solid angle equal to dA by r square. Now we want to learn what are the solid angles made by this sphere, that is a spherical surface. Now first I have to calculate the total area. Total area is 4 pi r square. Now in order to calculate the total solid angle, that is omega equal to area by r square. Now area equal to 4 pi r square by r square, r square cancel, so that is 4 pi. Okay, now for the second case. Okay, so omega for half hemisphere, and okay, so part of total sphere, so it's a hemisphere, so that is equal to 2 pi r square by r square, r square cancel, that is 2 pi. Okay, now for 1/4 of it, 1/4 of a sphere, if we take just slice the watermelon in 4 parts, so what will be the value for omega for 1/4 will be pi r square by r square equal to pi. So this is how we get the solid angle just by calculating the area of the surface by r square. Is that clear? Now my question is, does it really matters if it is not a sphere but any other shape? Like if I just change the shape of the solid sphere instead of taking a random shape, there also the total solid angle is constant. Why? Because this ratio is constant. So that is why it doesn't matter what is the amount of area you are getting. It depends upon how much solid angle is making over the center. So that is 4 pi for any kind of random shape. If we just total closed surface, for a total closed surface the solid angle is 4 pi. Okay, now let us try to move on and find out the relation between this area vector and the solid angle. Now in order to understand the relation between the area vector and the solid angle, here also we will try to take a cone like this. Okay, now please try to understand the center of the cone is O and the surface is this vector dA. This is the top of the cone. Now this is the radius r and this r cap is the radius vector which is in the outer direction from the center. Now in order to take the omega, d omega, that is the solid angle, what we have to do, we have to take the component of this dA vector in the direction of the radius vector. So if this angle, the angle between this r cap and dA is cos is theta, then the component of this dA vector in the direction of the radius vector, that is dA cos theta. Okay. Now solid angle d omega equal to dA cos theta by r square. So this is how we can calculate the solid angle. Is that clear? Now there is another alternative option. Instead of calculating this cos theta component, cos theta, we can simply make them dot product. So d omega equal to dA dot r cap by r square. So this is how also we can find out the solid angle for this cone. So this solid angle we are calculating over here actually. So I hope still now you have understood the area vector and the solid angle. Now we are about to learn the concept of electric flux. That is the main focus of this chapter. So let us start. Now in order to understand the concept of electric flux, I would like to give you an example. Suppose water is flowing and fishes are moving inside the water, and I have a surface by which I have a net by which I want to catch those fishes. Okay. So if I try to catch those fishes by a net, if I try to orient the net in this direction, in the horizontal direction, am I able to catch any fish? Answer is no. But if I try to orient the net in this direction, then only I can catch those fishes. Why? That is because the motion of the fish will try to oppose the motion of the net. Now I would like to give you another example. See, there is a torch and I want to orient the light like this. It will be acquiring less amount of area, or in this case it will be acquiring less amount of area. Here it is greater amount of area it is taking, but here it is lesser amount of area it is taking. Now if I just try to orient the light in this direction, although light is there but no light is falling on the board. So from these cases you can see that it doesn't matter what is the amount of area and what is the amount of field, but it matters what is the angle between the area and the field. So what is important in case of vector field, so flux of vector field, the number of field lines passing through the area. Try to understand. I have a vector field lines which is represented by these 4 parallel lines, and I have a area like this. Now if I am orienting the area vector like this, and which is the normal of the area vector is in the parallel to the field. In second case, I am orienting the area vector like this, which is in the making an angle theta with the vector field. So in which case greater number of vector field lines will pass through the area vector? In the first case. So in this case greater number of vector field lines will pass through the area vector. But if I take the vector field lines like area vector like this, which is extremely perpendicular, the normal is perpendicular to the vector field, then no lines of force will pass through the area vector, isn't it? So what I can conclude that the component of the area vector, that is a cos theta, is important over here. Okay, and in order to calculate this flux, which is represented by this phi, that is equal to E, that is the vector field, into a cos theta. Okay, E into a cos theta. So that is equal to E dot A, that is the flux. So what I can conclude from here, the dot product between the area vector and the vector field is the flux of that field. Is that clear? So this is how we get to know about the concept of electric flux. Now let us try to understand by two cases. Okay, in the first case, if the angle between the area vector and the vector field is 0 degree, that means this theta equal to 0 degree, as I said before. So if the angle is 0 degree, that means the area vector is actually parallel. The area vector is actually parallel to the field vector. Then what will happen? Then cos theta equal to 1. So phi equal to EA simply. But in the second case, if theta equal to pi by 2, that is 90 degree, then cos theta equal to 0. In that case, phi equal to EA into 0 equal to 0. So this is how we can conclude that in order to calculate the flux, not only the vector field, not only the area, but also the angle between that two field is, angle between the area vector and the field is important. Is that clear? Okay. Now let us quickly move on to the next topic, that how we can calculate the area for a non-uniform surface. Now our target is to understand what will be the electric flux for non-uniform field and surface of arbitrary shape and orientation. Now what does it mean for the non-uniform field? It means that somewhere the field is stronger, somewhere the field is less stronger. Okay, and the direction of the electric field is also not in single direction, it is moving like this. So let us try to represent the field like this. So this is quite non-uniform field. Okay, so non-uniform field represented by defined lines which is not parallel. Now arbitrary shape, what does it mean by arbitrary shape? We are not sure about the shape of the surface for which we are trying to calculate the electric field. So this is quite arbitrary shape. Okay. Now for this non-uniform field and for this arbitrary shape, I want to find out the flux. Am I able to find out the flux? Yes, but whenever there is a non-uniformity and randomness in the shape and the orientation, arbitrary, and orientation is also arbitrary and the shape is also arbitrary, what we have to do? First we have to find out the differential form of the flux, that is d phi equal to E dot dA. So this is the differential form of the previous equation. Now I have to integrate this. So this is integration and then it will be E dot dA. So this is a area or surface integration represented by this A. So this is how we can calculate, but without any given data, without the nature of the electric field, without the nature of the shape and the size of the surface, I cannot calculate or evaluate the value. But still now I can say that for total flux phi equal to E integration of E dot dA. Is that clear? Now let us come to another very important point, that what will be the total flux for a area which is a closed one. Still now we are discussing about open surface. Open surface, what is the meaning of open surface? Which we can close by a contour, means by a line we can close this surface. Okay. But what happens if the surface itself is closed? That means, what is the example of closed surface? Like a sphere, like a room. So these are the example of closed surface. And what is the example of open surface? Like a field or like a dish. These are the examples of open surface. So still now we are discussing about open surface. Now we want to learn what will be the vector electric flux for a closed surface. So in order to understand the flux to a closed surface, we have to take a potato. Okay, potato is a good example. So let us take a potato of arbitrary shape, and this is presence inside a electric field. So electric lines of force goes in and out of the potato, that means the arbitrary closed surface. That is what we are talking about. So we have to calculate the total surface integration. What is the total surface integration? Total surface integration is represented by this. Any kind of total integration is represented by this. Okay. So total flux phi equal to total surface integration. This ring represents the total and S represents the surface. So total surface integration of electric field multiplied with the area dA. So this is what we get for the closed surface, electric flux through a closed surface. So from this point there must be a dot product, actually I forgot to mention. So from this point we are about to start the concept of Gauss theorem. So in Gauss theorem we are interested about this little thing, in the total surface integration of A dot dA. We will start from this point in case of in the mathematical form of Gauss theorem. So thank you for watching. I think I am able to clear you about the area vector, about the solid angle and electric flux. So this was the topic of discussion of this chapter, of this video. So in the following video we will be learning about Gauss's theorem. So thank you for watching, and please keep continuing watching this video. I think in this lockdown period these videos will be helpful for you to understand the class 12 physics, concept of 12 physics in a better way. So thank you for watching. Bye bye, take care and stay safe.